Hello everyone. So far we've been looking at different type of waves, transverse and longitudinal waves. The problems that we dealt with were 1D problems mainly, and we used boundary conditions to solve these problems. So basically what I'm be doing today is applying similar techniques in order to solve a more complicated problem that is a 2D problem. I also want to focus on a different type of waves. It's quite general type of waves that is known as acoustic gravity wave. If I wanted to summarize what an acoustic gravity wave is, you can think of a sound wave, just as when we discussed longitudinal waves in a flute or in a pipeline. So these sound waves are compressing the medium as they're traveling. But when we normally talk about sound waves, we ignore gravitational effects. So now I'm speaking, I'm generating these waves. For many practical reasons, you can ignore gravity. Okay, so gravity won't really affect the properties of the sound that I'm producing. Acoustic gravity wave is about the type of waves that are generated in a medium just like air or water, but under the effects of both gravity and compressibility. Regardless to whether these waves would be modified, the properties of the waves would be modified due to gravity or not, that's a different practical question. So when we talk about acoustic gravity waves, so you can simply think that we talk about waves that are generated in a medium, a compressible medium, and we do include the gravitational effects on that wave. Now, just to give you an idea why is that important or when is that important, if you have an earthquake, for example, you're basically the generated waves, not only the tsunami, but there's all the sound that is generated, the noise in the ocean, it has a wavelength which is very, very long. We're talking about tens of kilometers in terms of a wavelength, 50, 60, 70 kilometers in a wavelength. At these lengths, gravity becomes important. So there is a modification of the properties of this type of sound waves, very long wavelength. Alright, so that's it for the physical introduction. As we progress, I will discuss the new things as we go. So the problem that we have is the following. It's a boundary value problem. So we have the ocean here, so it's the physical problem. This is the sea surface. This is where you can generate the tsunami, for example, or the surface gravity waves. By the way, they're called surface gravity waves. There are two parts. And the first part is quite obvious. The surface is because they are generated at the surface. Okay. Wind is generating them, for example, can be other sources. Wind is generating them, so the inertia wants to move them, but gravity wants to restore them, right? And that's why we also call them gravity waves. So these are surface gravity waves, because the effects of gravity are very important in the dynamics of these waves. You can't ignore gravity here, definitely not. This is the seafloor. The seafloor can be very complicated, and depending on the seafloor, the solution can be very simple to almost impossible to solve. It really depends on what's happening at these boundary conditions. We will assume that the interior of the water is governed by the wave equation. But it's not a 1D wave equation, obviously. Now we have a 2D problem. So if I put here, I'm going to use x and z. So z would be the vertical axis and x would be the horizontal. right? So it's a 2D problem. And the frame of reference, I will take it at the surface. Okay, so this is Z, and this is X. You don't have to take the frame of reference at the surface. You can take it anywhere you want, depending on the problem. In fact, many times we take it also at the seafloor. As an example, if you're discussing movements of the seafloor, sometimes it's convenient to have it at the seafloor. But if you just want to analyze the type of waves that can exist there, you can take it either here or at the seafloor. It wouldn't really matter. Okay, so we have these, at the surface we have the surface gravity waves. I can write these here. So we have surface gravity waves, and in the interior, because of we allow compressibility, I'm gonna write the assumptions later on, or at least discuss the assumptions. We will allow the compressibility of the interior of the water. We assume the fluid is water there, which means that we can have also sound waves. Okay, the acoustic part of the problem here. So you basically allow all kind of sound waves to propagate. Okay, so this would be the acoustic waves. I'm going to already type acoustic gravity wave. Okay, acoustic gravity wave. And many times for the surface wave, the tsunami or the water wave, or the people call it gravity acoustic. The reason is just to highlight that you consider the gravity wave, and you also consider the compressibility effects on the gravity part. Now let's go one step back and discuss these two type of waves and see how separate they are normally, and why normally people discussing one wave they don't look at the other wave. So when you're discussing gravity waves, like the water waves, let's say the short regular water waves that you see in the ocean. When you go surfing, you don't want to see a tsunami. So when you're talking about these waves, the compressibility of the water practically does not add anything when you're solving the equations. It's minor. It's negligible for most practical reasons. So you don't really need this acoustic term, or the compressibility of the water, in order to describe the dynamics of the gravity waves, surface gravity waves. Now, and vice versa, is when you talk about acoustic waves, sound waves here, as I said at the beginning, you don't really need the gravitational effects. So you could ignore gravitational effects. You don't have any effects of gravity there, so basically there is no, it's just a rigid surface there. And you're talking about sound in a pipe or something like that. Okay. But what we're gonna do now is really solve everything together. I'm gonna show that the solution is a general solution. It's quite elegant, and it gives a solution for the surface waves and for the acoustic gravity waves with the corrections. And later on, I will show you why we actually do that. So what practical reasons we have that we do that. Okay, so let me discuss some of the assumptions, and then I'll write these the assumptions and the boundary conditions, and then I'll write these for you. First, I want you to concentrate on this so you fully understand the picture. If we have a wave equation here, and this is something that I can already write, I'm going to write it with phi. I'm going to explain what is phi later on. Okay, I'm going to write now. It's a 2D problem, so we have d squared phi dx squared plus d squared phi dz squared equals to 1 over c squared d squared phi dt squared. Now, first of all, the first thing that you're supposed to notice now that this is a wave equation. You don't really care if this is c or v or any other letter, right? And you also see that this is the space derivative with respect to space, and this is the derivative with respect to time. And this is all what matters mathematically. Okay, so this is the wave equation. Now, c here is the speed of sound in water. Okay, so this is speed of sound in water, which is about 1,500 meters per second. If you think about it, this is quite high speed. It's 1,000, of course, is much higher than the speed of sound in air, because the density of the water is larger. So for the interior, we assume that this wave equation can cover the interior of the fluid. And this is a good assumption. Now, what I'm not going to show you, because it's not the scope of this module, is how you get this, how you derive this equation for this problem. I hope you're convinced that we've seen that for wave problems, the wave equation is a good equation to deal with it. So this is the main, the governing equation for the interior of the the water here, okay, the fluid. Now we have to solve this. Now we know the general solution for this, but to solve this we actually need the boundary conditions. So it's all about the wave equation and the boundary conditions, as I mentioned in the past. What are the boundary conditions? Let's think about this first, and later on I'm going to write this down. The seafloor here can be anything really, almost, in terms of the topography, and we're gonna keep things simple. So we talk about constant depth, and believe me, this is not a bad assumption. In many places in the ocean, for these scales that we're talking about, the tsunami scale and it's very, very large scales, the average depth of the ocean is 4 kilometers. And the changes in the seafloor in many places is almost constant. So it's a very good assumption. Okay. Let's just put here assumptions. Okay. So we said we have compressible ocean. The water is compressible, and the depth is constant. So water depth is constant. I'm gonna make another assumption here, because still with this, even when the depth is constant, you can have very difficult problems. If you had an elastic seafloor, which is normally elastic medium, that would complicate things. I can already tell you that to solve it, you would require 2 more equations like this one in the elastic part, and then more condition to what happens deep in the elastic part. We are not going there, not at all. We're going to keep things as simple as possible, without giving up the main physics. So we do consider the problem with constant depth, but we're going to make an assumption which makes our life really easier, and that is that the seafloor is rigid. Okay, so this is rigid. Write it here. Rigid seafloor. Now again, the challenge is to translate the physics into mathematics. What does rigid mean? Rigid means that you cannot penetrate through it. So if you think in terms of velocities or position, as we had the masses and we always looked at the positions and how they were moving, things can go here up and down, right? And they might go also right and left. But when it comes to the bottom here, they won't be able to go down. This is the meaning of rigid. You cannot penetrate through them. So to translate that into mathematics, I would say that the velocity in the z direction, w if you want, is 0 there. Okay, for any x, right? For any x, anytime, the velocity there is always 0. Okay, so I'll type that later on mathematically after I explain about the phi here that is describing the interior of the medium here. What happens at the surface? At the surface we have two conditions. At the end of the day, you need one condition, that's the combined condition, and you don't really need to know how we derive it, but I want to give you some idea about the physics behind it, just to think about it. At the surface, the first condition is called the kinematic condition. The kinematic condition says that this is eta, okay, so this is the surface here, z, is at eta. And the eta is a function of x and t. Right? What it physically says is that if you have a particle, fluid parcel at the surface, it would remain at the surface forever. In other words, you can think of the ocean as streamlines, okay? And they cannot cross each other. You can have movements, so you can have things like this. So these are the streamlines actually that they have here, okay? I have all these nodes here. Each one of these is a streamline. You can make all kind of shapes with it. That would be the waves, but they will never cross each other. Okay. So a particle on a streamline would remain on a streamline, and at the surface, if you have something at the surface, therefore it will never find itself inside here in the interior. It will always remain at the surface. Right? This is the first, this is called the kinematic condition. There's another condition which is called the dynamic condition. And the dynamic condition basically governs the, you can think about it as Newton's second law. Okay? So it governs the propagation at the surface. If you want a little bit more, I'm going to write down the conditions. Okay, so let's summarize. Before I summarize, actually I want to talk about this phi. Phi is called the velocity potential. So phi is the velocity potential. And the velocity potential, if u is the velocity vector, then the velocity potential is simply the gradient. The velocity is the gradient of the velocity potential. Okay, so I can write, for example, u would be d phi dx. V, the velocity in the y direction, we don't have it here, but just to you see the picture, and then w, the velocity in the z direction would be d phi dz. Now this is a definition. I'll tell you why we do this, but this is first of all a definition. So you can define it as plus or you can define it as minus. It doesn't matter. As long as you're consistent, it shouldn't matter. Okay, so you can have here plus or minus. I'm gonna write only minus now, like this, so it doesn't confuse you, because it's important. If you decide it's a plus, it should be always a plus for that problem. Okay, if you decide it's a minus, it should always be a minus. But you can decide whether it's a plus or a minus. Why do we do that? Now, remember in the problem that we've been looking at, we wanted to find the position, for example, of the mass, something like that, at any given time. So to describe the problem, you want to look either at the position, or you want to look at the location, at the velocities, and so on. We could look at the velocities really, but these are vectors. Now when it's a 1D problem, it doesn't really matter. This is a 2D problem now. If you define the potential in this way, you would be solving the problem in a potential form, and a potential is a scalar. So you won't be confusing with directions and right, and vectors, because it's a scalar problem now. So you solve everything with the potential. At the end, you go back to this definition. You say, oh, I want the velocities. I take the derivative after I found the potential in x. That gives me the velocity in u. I take the derivative in z. That gives me the velocity in the z direction w. Right? All right. So now, if we look at the rigid bottom, for example, the no penetration condition at the rigid bottom would say that the velocity in the z direction, w, which is basically d phi dz, if we define it positive, d phi dz would be equal 0 there. So I can simply write here that d phi dz here equals 0. So this would be my condition at the bottom, for the rigid case. Let's write down the two conditions, the kinematic, dynamic conditions at the surface, make a combined conditions out of these, and then we're ready to go and solve the equations. So the first condition is the kinematic condition. Kinematic condition, as I said, is z equals eta, and eta is the surface of the water. So we can write z equals eta of x and t. So if I take the derivative d z dt, that gives d eta dt plus, I'm going to write it in general first, and then we can consider this case. So we have u d eta dx plus v d eta dy plus w d eta dz. Now notice first that eta is not a function of z, right? So this is 0. And in our case also, it's a 2D problem, there is no y component, so this also would fall. Okay, so this is also 0. But in addition, we are solving only linear problems. We are not looking at non-linear terms, and this term is non-linear. You see, you have u times d eta dx. This is a non-linear term, okay? So this is non-linear, and therefore we also neglect it. So the condition is, I can write, and what is this? This is the velocity, right? dz dt is the velocity in the z direction, which is basically d phi dz. So not to confuse you, we're gonna let's say we choose plus. Okay, you can just put a plus also if you want. We have to be consistent now. Okay, so if it's a plus everywhere. Which means I can rewrite this as d phi dz. It's lots of derivatives here, so instead of writing d phi dz and the d phi dx and so on, I'm going to make a short notation. So I'm going to write phi and small z here. I hope you know that this means d phi dz. Okay. So d phi dz would be d eta dt. Same thing. This is the partial derivative here. These subscripts here for the partial derivatives. So this would be the kinematic condition. Let's look at the dynamic condition. This is the kinematic condition. The dynamic condition at the surface. At the surface means that we're talking at the frame of reference we have is the surface means z equals 0. So this is at z equals 0. And the dynamic condition is also at z equals 0. So what do we have here? At the surface we have the pressure, which is a function of x, y, z, and t. You can write it in general again for you just to know. We don't have y here in this problem. And z would be at eta, right? Z at eta at time t. The pressure at the surface is atmospheric. The dynamic condition. And then from Bernoulli equation, if you don't know how to get there, that's completely fine. You're going to use the conditions as given at the end of the day. So the phi dt plus half gradient phi squared. This would be the term with the kinetic energy, for example. This would be the pressure, and here you have the potential term. This would be constant, this whole thing. This is just a function of time. It's constant in space. So if you take the gradient of the whole thing, this would be 0. Okay, we finally end up this term is this is nonlinear, right? So this is higher, this is nonlinear. We neglect that term. This is gz, right? Or g eta. Z is eta, right? And the pressure is atmospheric. So we can finally write for the dynamic condition d phi dt. So phi t plus g times eta. These are the two terms that survive. Right? This is atmospheric. So there's no change across the surface. Equals 0. This is the linearized condition, dynamic condition. Alright, so we have two conditions now at z equals 0, and what we want to do next is to get the combined condition, which is quite easy. All you need to do, you see, you have eta here, and you have eta t here. So if you take the derivative in time here, you get eta t here, right? And then you can substitute back there, and you have the relation with phi only. We don't want to carry the etas. So the combined condition, it's right here, combined condition I'll take this and take the derivative in time, so phi tt plus g eta t equals 0. This is the first equation. I'm gonna type down this equation here, which is phi z equals eta t. And they're both at z equals 0. So if I substitute eta t here, all I get is phi tt. Let's do it. Get phi tt plus g phi z equals 0, and this is at z equals 0. So this is the combined condition. Okay, so what do we have now? We have all three equations that we need, so the governing equation and the combined and the boundary conditions. I'm going to write these up there and then solve these equations, okay? So we put them here. So we have phi xx plus phi zz equals 1 over c squared times phi tt. This is at z, which is between 0 and minus, between, we need to, between 0 and minus h, and h is constant, so this would be h, is the depth. And the boundary conditions, the combined equation, which is right here, so it's phi t plus g phi z equals 0. This is at z equals 0. And the other condition is simply phi z equals 0. It's this condition at z equals minus h. Now at this stage I want to make one further simplification. So basically we're not going to solve the wave equation initially, but I want to do that. I'm going to assume that the water is incompressible. The meaning is that the water is incompressible, that if you try to compress it, every movement is, if you make one movement in one place, the flow in all the places would react instantaneously. Okay, which means, in other words, the speed of sound, if you want, is infinitely large. If the speed of sound is infinitely large, this term goes to 0. So this is 0, which means we don't have the wave equation. This is the Laplace equation. It's a different equation, but we're going to solve it. It's going to give us a nice solution for the gravity wave initially. All right. What do we need to do to solve the equation? First thing, let's make an assumption about the eta, about the surface. We assume that the surface is behaving in a sinusoidal way. That would be the solution for the wave at the surface. So we can write these down about the surface. So I'm going to add this here. So eta would be something like eta 0. I'm already in the complex domain, so e to the power I kx minus omega t. The next step would be, remove this, the next step would be now to solve the equations, to do something which is called separation of variables. So I have the function phi, which is a function of x, z, and t. And I assume that the solution would behave like this A time in the sense that is oscillatory in the x direction, but I separate between the x and z directions. So I assume it's a product of two independent functions. So I can write down some constant times f of z times e to the power I kx minus omega t. Now I substitute this into the field equation, or the governing equation. Let's call this 1, 2, and 3. So I substitute this into 1, and what I have is the following. On the right hand we have a 0, and at the end of the day we will have that exponent which would we can cancel out. So what's important now is if I look at the derivatives, we have the phi xx. From phi xx I get a minus k squared times f. So minus k squared times f. And from the other term, we have, this is f of z, this is not a function of z. I will have plus phi zz, and this is equal 0. Everything else would be cancelled. A and the exponent would be on both sides. I hope you see that. So this is what we get from the first equation. And the solution for this, I can rewrite it if you mix it in this form. Now the general solution for this equation, a general solution, is of the form f equals some constant c1 e k to the power e to the power kz plus c2 e to the power minus kz. This is the general solution for this differential equation. All right. In the same way that I have this equation in terms of f, now I want the boundary conditions also in terms of f. So I can have from the second equation, for example, if I substitute phi into the second equation, the boundary condition, we have phi tt, that gives us a minus omega squared. I want to divide by the g already. I have a minus omega squared over g times f. And then we have phi z, that would give us f of z plus f df dz equals 0. So this would be the second differential, the boundary condition now that we're going to use. I can rearrange it as fz, if you want, minus omega squared over g times f equals 0. Okay, so this would be the 2 star, and let's call this 1 star. And this would be 2 star. The same thing with the bottom boundary condition, and the bottom boundary condition would simply give me, I already write it, that f df dz equals 0. This is equation 3 star. Now it's important to note that this is at z equals minus h, and this is at z equals 0. I said this is the general solution. In fact, each term here would satisfy this equation, and you can see this immediately. If you take the second derivative of z, that will give you a k squared times f, minus k squared times f gives you 0. Each one of these would satisfy it. So this is the most general solution. So far so good. What we do next is substitute into the boundary conditions. We make use of the boundary conditions. So let's make use of the bottom boundary condition first. So from 3 star, fz equals 0 at z equal minus h. Let me take the derivative first, actually. So what is fz? Fz is k times c1 e to the power kz minus c2 e to the power minus kz. This is fz in general. I can delete this now. So now I want to make use of this boundary condition. I know that fz equals 0 and z equals minus h. Yeah. So this is 0 from the 3 star. What we get is that k times, the k is going to fall. I hope you see that. It's going to be equal to 0. But I'm going to write it anyhow. K times c1 e to the power k times minus h. So e to the power minus kh. I'm substituting at this point, this depth. Minus c2 e to the power minus is going to be a plus kh here. And this is equal 0. So from here I get a relation between c1 and c2, between these two constants. And you can see this immediately, that c1 is c2 times e to the power 2kh. Okay, now we go to the second boundary condition. So 2 star. We do the same thing, we substitute there, but now we know that c1 is c2 e to the power 2kh. So we can already substitute that as well. So now we're looking at here. Fz, I wrote the Fz here, the general one. So we're going to have Fz, which is k times c1. Now we're looking at z equal minus z equals 0. So this is 1 and this is 1. So c1 minus c2. I'm going to already substitute what is c1 here. So we have c2, this is our c1 e to the power 2kh minus c2 all minus omega squared over g times f. Now what is f? F, we go up here, but it's f at z equals 0, right? So we multiply by c1 plus c2, that's all, because this is 1 and this is 1 at z equals 0. But what is c1? c1 is c2 e to the power k 2kh. So I can already write it down here, c2 e to the power 2kh minus plus c2. And this would be f at z equals 0. This whole thing is equal to 0. Now, look at this. We lose c2. So by substituting to the boundary condition, that doesn't give us c1 and c2. But it gives us something not less important, and that is the dispersion relation. A relation between omega and k. And you can see this here. And this is what we're after now. So if I put omega squared on one side and the rest on the other side, I get g times k, and here I will have e to the power 2kh minus 1 divided by e to the power 2kh plus 1. And this is nothing but hyperbolic tangent of kh. So we have the dispersion relation, omega squared equals to g times k hyperbolic tangent of kh. Alright, I made some space here, and I also moved the dispersion relation that we derived here. I want to put also the potential, because at the end of the day we're after the potential. I want to put it here. I'm gonna keep that up to you to derive that, but all you need to use, let me see if we have it here on the wall. So all you need to use in order to get the potential, so you have this. This is the potential, right? This is F. Now we have F here with C1 and C2. But you make use also of the fact that I'm gonna add it here, eta t, right, equals to phi z. So making use of these, now you should be able to derive the potential, which would look like this: minus I omega eta 0 over k times hyperbolic cosine k z plus h divided by hyperbolic sine of kh e to the power I kx minus omega t. And to get the back to the real problem, you need to take the real part. If you do that, the real part would be, don't forget, when you make a cosine and the sine here, you have to take the sine part with the with I here, with the imaginary part, and the reason is that we have I there, and at the end of the day you want the real quantity. So that would give you phi, which is omega eta 0 over k cosine h k z plus h divided by hyperbolic sine z plus h sine kx minus omega t. Now all you need to do in order to get the velocity in the x direction is take d phi dx, and for the velocity in the z direction you take d phi dz. Alright, let's look at the dispersion relation a little bit. What happens when kh is very large? So if in the case that kh is much larger than 1, in other words, you're looking at a deep water problem. The deep water problem doesn't mean that the ocean is deep, I remind you, because if you have a tsunami, even if you have a 4 kilometers of depth, that is a shallow water problem, because the wavelength of the tsunami is much longer than the depth of the water. So a deep water problem has to do with both the wavelength, as you see here. Here it's basically the wave number, it's the same thing. It's 2 pi over lambda, and h. It's an interplay with these two. If kh gives you, or h over lambda is much larger than 1, then you see here from the hyperbolic tangent, this term would be tending to 1, to unity. And the dispersion relation in this case would be simply gk. So in this case, omega squared is simply gk. But if you take the other limit for shallow waters, so if kh is much smaller than 1, then the hyperbolic tangent here would tend to kh. So if I write it here, omega squared would be gk times kh, so gk squared times h. In terms of the phase velocity now, the first one, I remind you the phase velocity Vp or Cp, Vp is given by omega over k. So if you divide by k squared, you get g over k, and you take the square root, so you have square root of g over k. So if you want to estimate the phase velocity of waves in deep water, then all you need to do is take the square root of g divided by the wave number of these waves. On the other hand, in this case, so this is the first case is the deep, and this case is the shallow. In the shallow water case, what you would have now is you only need to divide by k squared and take the square root, so omega over k now is simply square root of gh. It's no longer dependent on the wave number, on the wavelength, as long as the wavelength is much longer than the depth. So we have a square root of gh. So in the case of a tsunami, for example, you talk about the shallow water, and you see from here that tsunami, the phase speed of the tsunami is independent of the wave number, and the phase speed of the tsunami is square root of gh. So if you consider, just to give you some feeling, if you consider the average depth in the water, which is 4 kilometers, so 4,000 meters, and take g as 10, so in the case of a tsunami, the phase speed would be 40,000 square root of 200 meters per second. That is a large number. This is a 720 kilometers per hour. It's almost like a jet plane. It's much higher speed than regular Cessna. So if you're flying your private Cessna and you see the tsunami and you think that you're gonna travel to the shoreline and alert the people there, it's not gonna work. With this speed, this can lead to catastrophic consequences, as we've seen in the Sumatra, for example, the Sumatra earthquake, Sumatra tsunami in 2004. Hundreds of thousands of people were killed because the tsunami was so large because of the earthquake, the nature of the earthquake that happened. But because it was quite close to the shoreline, it left no alarm time for the people to, in some places it was just a few minutes before it reached the shoreline, since the earthquake started. Alright, we will continue with the next problem. We have to leave now.